It'll be kind of quick on that. So first of all, this is actually Unit 5. Unit 5. Well, there might be a few questions on the next steps about it. But basically charge. Atoms have a positively charged nucleus, negative charge to the outside, all that. All electrons have the same mass. All electrons are the same. They're all negative. Why are electrons negative? Because they're electrons. We don't know why they're negative. It just is. It's the way the universe works. Electrons are negative. Nucleus has protons and neutrons. Protons are all identical. Neutrons are all identical. On that. Protons are 2,000 times more mass than the electron. They have a positive charge. Why do they have a positive charge? Because they are a proton. Why that? A neutron is slightly greater mass than a proton. It has no charge. Basically, the neutron is greater in mass than a proton by 1 electron. Basically, that's what a neutron is. A neutron is a proton and an electron stuck together. Because during beta decay, the neutron will spit out a beta particle, which is an electron, and transmute into a proton. We don't know. That's the weak nuclear force. Weak nuclear force is what holds those together. We don't know how that works yet. But it has something to do with how the electron and the proton stick together. And obviously how it spits it out during beta decay on that. Charged objects, if you have one more electron or one more proton, you have a charge. Now, you always keep in mind, the way the book explains it, it's very confusing. Remember, only electrons move. Okay? Either you gain electrons or you lose electrons. Positive charge never moves from object to object. Protons are in the nucleus. Because if I lost a proton, say if I'm iron and I lose a proton, am I iron anymore? No. Would that be a bad thing? Yeah, that's nasty things happen when we start losing protons. Start spitting out protons on that. So you are moving electrons. You have more protons, you're positive. You have more electrons, you're negative. The whole idea. Those of you in chemistry like ions, but on a more macro scale. If I rub a balloon on my head, I'm going to scrape electrons off my hair onto the balloon. So my hair becomes more positively charged, the balloon becomes negatively charged. I know that because the rubber likes electrons more than my hair does. On that. Measuring charge. When we measure charge in coulombs, our symbol is a great big cap, is a Q or Q, which is funny because it's the same symbol as heat. Even my symbol for charge, symbol for heat are the same symbol. We both use Q. I don't know why. We both use Q. But our unit here is the coulomb. Coulomb, right? Capital C. Coulomb. How many charges? And a coulomb is an enormous amount of charge. If you have 1 coulomb of charge, it's an enormous amount of charge on that. Because the fundamental charge, 1 proton or electron, we say that's an E. Our unit is the coulomb. 1 point. Well, they're not really taking notes. We're just talking, fundamental charge. Let's see. Make sure I get this number right. This is a number you should write down on that. All right. Fundamental charge. Okay, 1.6 times 10 to the minus 19th coulombs. This is the charge of 1 electron or 1 proton. You can see, to get to 1 coulomb, we need a lot of them. Yeah, so, but this is the charge. But Coulomb lived long before they understood where the charge was coming from. Coulomb is like the same time as Newton. Coulomb was around, that's the guy who did all this stuff. He's about the same time as Newton. It wasn't until, which is like the mid-1700s, it wasn't until the late 1800s they discovered the electron, and the early 1900s discovered the proton. So it was like almost 150 years later to figure out what it actually was on that. By the way, all these terms of proton, positive charge, negative charge, anybody know who first called charges positive and negative? Who the father, basically, who the Isaac Newton of electricity is? Yeah. Someone we don't think of as a scientist in the United States. He was an American. Well, he lived a long time ago. Put it this way, when you get pieces of paper with his face on it, you are very happy. Benjamin Franklin. Benjamin Franklin is basically the father of basically electricity. He's the one who coined the terms of positive and negative charges and things like that.
Did the key?
Yeah, well, we don't know if he actually did that, but yeah, but he did a lot of work with electricity. Keep in mind, the reason he was the guy sent to France to get help is because he was a world famous scientist. He was the only guy. We think Jefferson, those guys being really famous, they were nobodies. No one knew who they were outside the United States. Franklin was known all over the world. He had a reputation. He had a name. He could get help where the other guys couldn't. That's why he was the guy sent over to France to get help. He was the man. All right. Conservation charge, just like matter and everything else, you can't create or destroy charge. It always goes from one object to another. If something becomes 1 coulomb positive, something else has to become 1 coulomb negative. Yeah, so they have to do on that. Okay. So, leads us with Coulomb's law. Coulomb's law, which is one of our fundamental laws. It's a fundamental force. Coulomb said the relationship between a charge and distance, electric force, just as Newton found the relationship between force and gravity. That last thing we talked about. In fact, the electrical force between two charges is directly proportional to the product of the charges and inversely proportional distance between them. F of E is directly proportional. Q1, Q2 over E squared. Does that look familiar? Looks a lot like universal gravitation, doesn't it? Because they have universal gravitation, fundamental force of the universe, is exactly the same mathematical relationship as the electrical force, fundamental force of the universe. They're both fundamental forces. They have the same mathematical relationship. Don't you like random things in the universe? So you also have a Coulomb constant. Now the Coulomb constant, we don't have a nice name for it, it's just K. And basically it's 9 times 10 to the 9th Newton meter squared per Coulomb squared. This is our value. Notice 10 to the 9th. Remember our other one was like 10 to the negative 16th or something like that. There, the universal gravitational constant, is to the negative blah 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 blah. Here. 6.6 times 10 to the negative 11. So you have positive 9th, negative 11. What does that say about electrical force compared to gravitational force? Way bigger. Electrical force is way more on that. And because of that, we can say we have gravitation matter. F of G equals G M over D squared. Electrical K Q1 Q2 over D squared. Right? It's the same idea. And it works the same. By the way, everything. The reason I can go through this quickly because everything we learned about this, as far as how it works, is exactly the same as electricity. It's just instead of masses, we now have charges. Yes, sir? For what? For K, Newton per meter squared per Coulomb squared. In other words, G had a kilogram squared on the bottom, you have a Coulomb squared on the bottom. That's the only difference. All right, I think that's it. All right, so you guys, one person each group, go to the box. Make sure your names are on. And get out stuff for our first set of notes. What? What? Throw your papers in the box, in the slot. Take your sheet, put it in the slot. Okay, get out a piece of paper for our lecture notes for today. So now we're back to standard 3. So remember, these notes we will collect at the end of when we talk about it, we'll collect them. They go in your classwork packet. These are lecture notes. Now, these are for our regular lecture notes. All right. You guys are cute.
I got like all the notes.
Dude. It's on the wall. I don't think you changed groups. You didn't change groups.
I can't see it's a public issue.
the lecture portion. So this is chapter 21. These are chapter 21 notes. Try not to get confused when we're doing things. Chapter 21. All right, so thermodynamics. This is what the next four chapters are about. What standard 3 is about. Thermodynamics. This is study of heat and how heat transfers from one object to another. And I put up T-dyes because that's how I usually abbreviate thermodynamics, because I hate writing out thermodynamics over and over again. If you are in college, you generally, if you're an engineering major, certain types of science majors, you will probably take a whole semester course on this. So, as an oceanographer, we studied a lot about heat flow. Being an engineer, we study, especially a naval engineer, a lot of how Navy ships run. You have to understand these thermodynamic processes, how car engines run, how jet engines run, steam engines. All has to do with thermodynamics. In fact, we're going to talk about internal combustion engines and external combustion engines and things like that. That's what we're doing. Anyone need more time? You had that look. Mary, the universal sign of text message. I couldn't believe you would be doing it right in front of me. But you've been on vacation for 18 days. And let's face it, your generation, how many hundreds of text messages do you send every day? What? A lot. Actually, I had a freshman last year who they were doing some article about her. She was like, for how many thousands of text messages a month she sent, like tens of thousands.
Imagine paying for all those texts.
Well, unlimited texting, I guess, helps, but still, I never caught her. She wasn't doing it in class, so a lot of them must have been like one word or something.
I think that's is that like
Isn't that what Facebook's all about? No social interaction.
just text.
Okay, are we here? Lots of talking, so we must be done. Okay. Chill. Okay, temperature. Temperature. Our symbol for temperature is a capital T. Capital T. Our unit. Well, the actual unit for temperature in physics is the Kelvin. Absolute scale is Kelvin. But we will also use Celsius, and we'll talk about why we can use Celsius, degrees C. So it's kelvins, no degrees, not degrees kelvins, just kelvins. It's our absolute scale. And temperature tells us how hot or cold something is, but we want to get beyond that. Specifically, it says what is the average kinetic energy of atoms and molecules in a substance. And since it is an average, how many molecules are we actually talking about here? 1. Keep in mind, when we talk temperature, we are talking about the average 1 molecule. Now, on that, the average 1. Average 1. By the way, the star readings, if you missed class a day, make sure you check the website to see what star reading was that day. You're still responsible for those star readings, even if you aren't here to do them. No, you do Cornell notes. You read it, and you do Cornell reading notes, which will turn you in when you get back to class Tuesday. No question. Just do a Cornell outline of the thing. All right. Does anybody need more time? Good? Any more time? So, when we're talking about this, right, the particles in all the substances are moving to some extent. Even this table, you might say, well, this table isn't moving. So if we got down the molecular level, down into the table, we would see that all the little molecules that make up the table are vibrating. They're locked together because they're solids, but they're vibrating within that matrix. On that, if you have a liquid, they're all moving around together. Gases, they're all moving around. Now, for energy, if you're talking about the same substance, a gas of a substance is going to be more energetic than liquids. It's going to be moving a lot faster. More kinetic energy, remember, energy of motion. Liquids are going to be more energetic than solids. Okay, so for water, gaseous water, steam, has more energy than liquid water. Liquid water has more energy than solid water, even if they're at the same temperature. We're going to learn that when we do phase change, because water, when you phase change, water, you have 0 degrees C ice, and you have 0 degrees C liquid, you have to add energy to go from ice to liquid. So these liquid molecules, although they have the same temperature, they're more energetic because they have that extra energy of phase change on that. Anyone need more time?
Eureka! The story so far. When matter, in any of its three states, gets hot, its molecules go faster and take up more space, and the solid, liquid, or gas expands. When matter gets cold, its molecules go slower and take up less space, and the solid, liquid, or gas contracts. And now, measuring temperature. Can you tell whether something is hot or cold? In that case, decide which of these three bathtubs you'd like to step into. This one, which is freezing cold, or this one, which is boiling hot, or this one, which is neither too hot nor too cold. It's an easy choice, isn't it? Well, go on. Step into the middle one. Feels just a bit too hot, doesn't it? Try the other foot. Oh, now it feels a bit too cold. Well, perhaps judging whether something is hot or cold isn't so easy after all. This is because the human body can only notice differences in hotness or coldness, how hot or cold something is in comparison with something else. But even your own feet can't agree about how hot or cold the water in the middle bathtub is. There must be a better way to measure degree of hotness, or temperature as we usually say. What do we know about hotness? Well, when the temperature of something goes up, its molecules go faster. The molecules in the boiling hot bath water are going too fast for comfort. And the molecules in the freezing cold bath water are going too slowly for comfort. If we could only make sure that the molecules in the in-between bath water were going at just the right speed for the human body, you could take your bath. But how can we measure their speed? The molecules are so tiny, we can't even see them, let alone clock how fast they're going. Wait a minute. There's something else we know about hotness. It not only causes a speed up of molecules, but this speed up causes matter to expand. So we could measure molecule speed indirectly by measuring the effect of that speed, the expansion itself. And that's exactly what a Swedish scientist by the name of Anders Celsius did in 1742. He took a liquid that expands quite a bit when it gets hot, mercury, and poured it into a little tube. He then put the tube into some freezing cold water, and the mercury contracted down to here. He decided to label this freezing point of water 0 degrees Celsius. Next, he put the tube into some boiling hot water, and the mercury expanded up to here. He marked this boiling point of water 100 degrees Celsius. Now he had a means of measuring the relative speeds of molecules. In other words, the relative temperature or degree of hotness of things. Comfortable room temperature is 20 degrees. But 30 degrees is a bit too hot. And minus 20 degrees is much too cold. Celsius could even take his own temperature and find it to be about 37 degrees, which, naturally enough, is the ideal temperature for your bath water, normal body temperature. All you have to do is adjust the water to 37 degrees, and you'll finally be able to take your bath, courtesy Anders Celsius and his hotness meter. Or if you prefer the Greek word for hotness, which is thermos, as in thermos bottle, his thermos meter, or thermometer. Is your bath water at the right temperature now? Oh my. Perhaps you should have taken a shower.
So, thermometers. Now, notice they talk about one type of thermometer. Lots of kinds of thermometers. In fact, for the most part, you are not going to be using thermometers that have like little red stuff in them, or green stuff, or blue stuff, which we call spirit thermometers because they're full of alcohol. If it was silver, it's probably mercury. We do not use mercury thermometers, even though they're more accurate, because if you drop one, we have to basically take apart the whole room, clean it up. We don't use it anymore. Spirit thermometers, drop them, clean it up, they're no problem. We won't be using those. For the most part, you're going to be using digital thermometers. Basically, it looks like a piece of metal, but it still works by expansion and contraction. They all do. Now, very early thermometers didn't really look like this, but worked on this principle. This is, if you can go out and buy one of these. They're usually decorative. They're called a Galileo thermometer. Why are they called? Because he developed thermometers similar to this, although it didn't have like a column like this. But what these do is you have a fluid in here, and each one of these little balls has a different kind of fluid, has a different density. As this fluid, the clear fluid, heats up and cools down, it becomes more and less dense. As it becomes more dense, the balls will start to float to the surface. Just like the Missouri up here floats. What can we say about the Missouri density of the Missouri compared to seawater? It's less. It is less dense than seawater because it's floating. So as the liquid becomes more dense, as you cool down, these will start to rise up, and you just read the bottom one. Now these have nice little pieces. Usually have a Fahrenheit scale. Galileo didn't have a Fahrenheit scale. So that's the problem. When he had his own scale, but sharing things. Everybody had made their own thermometer. In fact, in here, we could use the Dominic scale. We can make a thermometer, use the Dominic scale. But then again, if we try to talk about to some of the other classes, well, what does 100 on the Dominic scale mean to anything else? See, this is where widely used thermometer scales came in. I mean, the Fahrenheit was really the first widely adapted one on that. But how do you make a thermometer? Anyone need more time? And the thing to remember, as we go on the scale, when you change one marking on your thermometer, you go 1 degree, you're going to change a certain amount of kinetic energy. How much that kinetic energy is depends on what scale you're using. Because like Fahrenheit and Celsius, the markings are different places. So you go up 1 degree Fahrenheit, 1 degree Celsius. They do represent different amounts of kinetic energy, but they don't. But it is still a change in kinetic energy. Yes, sir. We'll talk about that in a minute. This is not your recap.
The difference between hot and cold are one of the first things we learned as humans coming into this world. As seasons change, so did the temperature of our surroundings. And it didn't take long for scientists to determine that we needed a way to measure the difference between what's hot and what's cold, so the thermometer was created. Well, why call it a thermometer? Well, thermo comes from Latin meaning heat, and meter is to measure, so simply put, a thermometer is a way to measure heat. But you don't need to be Galileo to make a thermometer. Come on, I'll show you what I mean. To build a simple thermometer, you'll need a clear bottle, rubbing alcohol, modeling clay, food coloring, a clear straw, and some water. Start by filling your bottle with equal parts rubbing alcohol and water, so the container is about 1/4 full. Add some food coloring so you can see the liquid better. Warning, do not drink this liquid. Wrap the modeling clay around the straw as so. The goal is to make a top for the bottle so the straw is suspended in the liquid but not touching the bottom. Seal the clay around the opening of the bottle so that no air may escape. Alright, we're done building the thermometer. Now let's see if it works. Heat up some water on the stove so that steam just becomes visible, and take the thermometer and place it in the water. Watch what happens. Hey, it works. The alcohol solution is flowing up the straw as the thermometer heats up. It works the other way too. Take the thermometer and place it in a bowl of ice water. Notice the liquid in the straw starts to fall now. So why does this happen? Well, if you look back to the egg in the bottle view do, the answer is the same. Expansion and contraction. As our alcohol solution heats up, it expands, forcing it to move up the straw. When it cools, the opposite happens. The fluid contracts and drops back down the straw again. So you may be wondering, why are we using alcohol in our solution? Why not just water? Well, two reasons. One, alcohol reacts more quickly to temperature changes than water, and it has a lower freezing point than water, allowing for measurement of temperatures below 32 degrees Fahrenheit. Yep, 98.6. So nearly 400 years have passed since the creation of the thermometer. It's interesting to know that the principles behind it are effectively the same. What's true then is true now, and Galileo himself would likely agree that this is a great one of life's little mysteries. For Viewdo.com, I'm Alan Cuccinelli.
What? It will if you get cold. Generally does not freeze in the temperatures that you would normally find in your house. I mean, if you put alcohol in your freezer, it'll get kind of slushy.
It gets slushy, but it doesn't get all.
But if you've got it colder, maybe it got cold enough, it's going to freeze. It's just, I think the freezing point of like ethanol is like minus like 30 Celsius, minus 20 Celsius, something like that. So it has to get pretty cold, yes. Well, he's just showing how to make a thermometer. I mean, there's other things going on that. The idea of something. But, you know, Dominic asked a question, where did these names come from? Well, we have temperature scales. Now, we're going to talk about three. Two we're going to use, one we're just talking about because that's what we generally use here in the United States. All temperature scales measure the same thing. And this is only three. There are more than three temperature scales around. In fact, there is an absolute scale for Fahrenheit. It's called Rankine scale. Rankine scale. We're not going to talk about that. But Rankine is to Fahrenheit what Kelvin is to Celsius. Okay, it's called the Rankine scale. But we're going to look at three scales. Fahrenheit, Celsius, and Kelvin. Like I said, we use Celsius and we use Kelvin. We're going to talk about Fahrenheit just because that's the one that is used in this country in our normal usage. And we're done. Good? Good? So, first thing we're going to talk about is Fahrenheit. Invented by David Gabriel Fahrenheit. Where it came from? He's got a name. He lived in Danzig, Germany in the early 1700s. Now, Danzig is on the Baltic. It's a port city. Anybody know what happens to the Baltic in the winter? It freezes. Which means if you are in Danzig, when it freezes, you ain't leaving until the spring. So it's kind of nice if you knew when it was about to start to freeze up. I mean, this is 1700s, early 1700s. Did they have icebreakers? No. I mean, wooden ships do not make very good icebreakers. You know, you need steel hulls. Even then, normal ships do not break ice. Icebreakers have very, very, very thick hulls, and they're very, very heavy. They get up on the ice and they crush the ice down. It's constantly running yourself up on the ice and crushing down, up on the ice, crushing down. They are extremely powerful ships. Very big ships. But this was based on an earlier scale by a guy named Romer. And we're actually going to see Romer later on with light. Romer was a guy who actually had a very early measurement of the speed of light. Pretty good, accurate one, too. But Romer was actually an astronomer. And the scales seem to have been influenced also by Newton. So these guys all lived at the same time. Coulomb.
Is this during the Enlightenment?
What?
Is this during the Enlightenment period? Enlightenment?
Enlightenment. Yeah, it's in that late early or late 16 to mid 1700s time period on that. So we have Romer, Newton, and it's also associated with the ranking absolute scales. Absolute scales, basically, it's an absolute scale. It means 0 on that scale is the coldest temperature possible. In other words, there is a point, because what are we moving? We're measuring kinetic energy. When we get to that absolute lowest temperature, it means the kinetic energy of the substance is 0. Which means the movement of the material. So, the little molecules, all the molecules are vibrating, the molecules stop vibrating. At least that's the theory. Trouble is you can't measure it. In other words, the act of measuring it puts in heat, makes it not absolute 0. But they've gotten very close. They actually have gotten things very, 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 very close to that. Anyone need more time? Good? So, on this scale. Now, some people, I've heard stories say, oh, he just kind of made the markings ahead of time, and then he put it in, and he found out where, like, freezing point of water, fresh water, and boiling point of water, but he made all the markings ahead of time. And that's not true. On the Fahrenheit scale, 0 degrees Fahrenheit and 100 were very specific temperatures that he wanted to mark. 0 degrees Celsius, or 0 degrees Fahrenheit. Fahrenheit is the temperature at which seawater freezes. Salt water. Salt water has a lower freezing point than fresh water. That's what 0 degrees is, because that's what he was really concerned about. He was concerned about when did the ocean freeze? Salt water. You have to get salt water down to 0 degrees Fahrenheit. 32 degrees. Pardon? Heats up. This is the freezing point, the freezing temperature. We'll talk about other things. These are set points. Freezing point of fresh water. And by the way, these temperatures are all sea level, as we're going to learn as we change altitude. We change them also. Freezing point of fresh water is 32 degrees Fahrenheit. 100 degrees Fahrenheit. He meant 100 degrees Fahrenheit to be normal human body temperature. Now we can say, oh, 98.6. We know now that there actually is a range. Normal, that's the average. Normal temperature is 98.6. However, some people are below, some people are above. Like for me, my normal body temperature is usually about 97.9. When I'm well, my body temperature is 97.9. Some people run higher than 98. They're always running about 99. So it's always a good idea. It's a good idea when you're not sick, when you're well, take your temperature in different parts of the day for several days, so you know what your normal body temperature. Because if your normal body temperature is 99 degrees, you have a temperature of 99.5. Are you really running a temperature? No. So if your normal body temperature is 97.5, and you have a 99.5 degree temperature, you're running. That's fairly good temperature starting to go there. Things like that. Yes, sir. Yeah, it might be that he was hot, or just how his scale, the accuracy of his equipment on that. It could be that his normal body temperature was 100 degrees. I mean, that's possible.
Maybe he was colder back then.
Well, this is also this actually occurred at the very end of a time called the Little Ice Age. It was a time of extreme global cooling at this time. The 1600s to the mid 1700s, late 1700s was a time period called the Little Ice Age. Time of crop failures. It's basically what pushed people to want to go to the New World. It's what pushed the French Revolution. This is what caused like all the starvation in France that fueled the French Revolution and things like that. You know, Marie Antoinette, let them eat cake. People were starving, but it was because there was extreme global cooling at that time. Climate is cycling. Goes up, goes down, goes up, goes down. 212 degrees Fahrenheit. 200 degrees Fahrenheit. This is boiling point of fresh water. Salt water actually boils at a little higher temperature on that. Okay, so this is Fahrenheit. Yes, sir. Well, this was the temperature scale that was used first. This was the first widely used temperature scale. And it's kind of associated with the English system. Yeah, well, you know, we still use the English system, right? Everybody else uses metric. But even in English countries, English-speaking countries, still sometimes, like in Australia, England, still sometimes you might see them give temperatures in Fahrenheit. But this was the first widely used scale. Celsius actually came later. Now, the Celsius scale, established by the Swedish astronomer Anders Celsius, early 1740s. This was after Fahrenheit. It's also called the centigrade scale. When I was in school, we called it centigrade, still degree C. Because the idea is they tried to adopt it, they wanted to put it into the SI metric system, even though this is not our SI unit of measurement. This is not the SI temperature scale. We will use it, and there's a reason we can use it, but it's not the SI system measurement scale. System International metric system. But back in the 70s, they called it centigrade. That's because it was on 100, just like metric 100. As a side, by the way, if you ever notice between, by the way, one of the Jeopardy questions, if you notice between the freezing of fresh water and the boiling of fresh water are 180 marks on the Fahrenheit scale. There's 180 degrees between it. In engineering, 1/180th of something is called a farad. From Fahrenheit, that's where it comes from. So that's a good Jeopardy question. 1/180th of something is called farad. Okay, anyone need more time? Yes, sir. Knots, nautical miles per hour. A nautical mile is 2,000 yards, as opposed to a statute mile, which is 1,760 yards. What? No, because it's not a water mile is longer. Because a water mile, a nautical mile is 1 minute of latitude. Latitude, latitude, longitude. Well, a degree of latitude is broken into 60 minutes. 1 minute of latitude is 1 mile. 1 degree of latitude is 60 miles. All right. So 0 degrees C. Now, Celsius actually, these were his set points. He was basing his on fresh water. The freezing point of fresh water. The boiling point is 100 boiling point of fresh water. Now notice 100 so there are 100 degrees between the boiling and freezing point. For Fahrenheit scale, for degrees Fahrenheit, there were 180. If I change 1 degree Celsius compared to 1 degree Fahrenheit, which represents a larger change in kinetic energy? Celsius, yeah, because we're dividing whatever energy it takes to go from freezing to boiling, we're dividing it by 100. On the Fahrenheit scale, it's the same amount of energy, but we're dividing it up 180 ways. So a change in 1 degree Celsius is a larger amount of kinetic energy change than a change of 1 degree Fahrenheit, because they represent different amounts of change in energy. Anyone need more time? These are all the values I'm giving you are sea level values. Sea level values. When you go up in the mountains, you notice it takes less temperature to boil something. Things will also freeze at a higher temperature. The freezing point of water is higher than 32 degrees in the mountains. Well, parts of it do, because it's too big. We'll talk about that later on, but Lake Tahoe is too deep. Maybe next week.
It's supposed to be colder next week.
It's all in Alaska. Some little town in Alaska has had like 18 feet of snow this winter already. And 22 inches of rain. They've run out of shovels and things like that. But the places are. Well, yeah, things like, but also like the boats in the harbor are sinking because they have so much ice and water and snow on them. The boats are actually sinking in the harbor. Okay, Kelvin. Now the Kelvin scale, developed by William Thomson, first Baron Kelvin. This was his title. He was a peer, a British English peer. In other words, he was a lord. His title was Lord Kelvin. So this is kind of like there's, well, you know, you have like dukes and earls. These are lords, you know. It's Baron Kelvin. And this scale is defined by absolute zero, which is that lowest possible temperature, and something called the triple point of water. Now, normally you can have, you know, at phase change you have like liquid water and gaseous water together when you're boiling. They're together. At a certain temperature and pressure, you're going to have liquid and solid together. At the triple point, at a particular temperature and pressure, all three phases are. So you're going from gas to liquid, liquid to gas, gas to solid. You have these phase changes all going on at the same time. At a particular, every substance has a triple point, but this is what's defined. And this is the SI unit of temperature. Kelvin is our SI unit. More time. So on the Kelvin scale, 0 Kelvin, absolute zero. There's zero kinetic energy left in the materials. 273.15 kelvins. Freezing of fresh water. Fresh water freezes at 273.13 kelvins. Water boils. Boiling of fresh water at 373.15. 272.16 is the triple point temperature. Just so we know. So it's near but there's also a pressure involved there too. But no, I want you to notice this. How many kelvins are between the freezing point and boiling point? There's 100 kelvins. There's a change. There's that change in temperature of 100 kelvins. But wait a minute. There was another scale that had a change in temperature of 100 to go from that same point. It's also the same as Celsius. Yes, sir. Do we have one unit of measurement for length? Well, different scales were developed at different times. I guess football just wouldn't be the same as 9.3 meters. Because 9.3 meters is the first down. Remember, they're just football players. Anyone need more time? Remember, these things are developed over time. Kelvin is after Celsius. So Fahrenheit, you have, and even before Fahrenheit, there was another scale by a guy named Romer, and there might have been something that Romer based his scale on. All right, we good? After. You probably have a little getting used to we have a very different schedule this way.
I would have been out by like.
Also, the fact that the first day you came back was our short day. All right, we good? Thank you. All right, so the Kelvin scale uses the same scale as Celsius. Now, Kelvin just took Celsius's scale and put 0 in another place. So that a change in temperature of 1 degree Celsius and 1 Kelvin are the same amount of kinetic energy. Which means when we do this, our temperature in kelvins equals the temperature in degrees C plus 273. So Celsius plus 273 gives you Kelvin. And if we use just a delta T, we're just looking at a change in temperature, we can use Celsius, because whether we use Kelvin or we use Celsius, it's still going to be the same number. A change in temperature of 100 Kelvin or a change in temperature of 100 degrees C, it's the same number. This is why we can use degrees Celsius in a lot of our formulas. Anytime we deal with a change in temperature, we can just use Celsius because it'll be the same amount. Now, the reason we have a different scale is because Kelvin was looking at the work of a guy named Jacques Charles. Charles was looking at what happens to volume and temperature. And notice that for gases, he had these charts, right? All these lines. It's a very linear thing that as you cool or heat up a gas, it expands and contracts. But he noticed if he extended all these lines down, that they all intersected at the same point. In other words, he theorized there is an absolute lowest temperature below which we cannot go, and that's which he defined as absolute 0. Which is why he did that. But all he did is take the Celsius scale and said, okay, instead of 0 being here, we're going to make 0 here. So the only difference between Kelvin's, the scales themselves, is just where we put 0. Okay, we just put 0 in a different place. Also, with the absolute scale, you never get a negative temperature. There are no negative temperatures in the Kelvin scale. Okay. Not really. We still use Celsius. We certainly don't get weather reports in kelvins. Right? All right. Questions? A couple more things, and then you can work on your little vocabulary things. All right, heat. And remember I said that heat, capital Q, our unit is the joule, or actually, I don't, all right, calorie with a little c. Calorie. Cal. Joule. Same joule we had before. The calorie. By the way, this is not a food calorie. This calorie here is not a food calorie. Your food calorie on a can would says, okay, this soda has 1 calorie. That's actually 1,000 of these calories. That's calorie with a capital C. Or a kilocalorie. Food calories are kilocalories. Now, This measures the energy that goes from one object to another object to a temperature difference. It's not the energy in you. It's when you put your hand on your table. Notice, if you put your hand on fire your table, what happens to your hand? It feels what? Cold. Cold. Because energy is leaving your hand into the table. Because your hand is warmer than the table, goes from your hot hand to the cold table. You're losing energy. That's the energy that goes to the table. Heat is not the energy in you. The heat is the energy that goes from one object to another because there is a temperature difference. That's a big thing. If there's no temperature difference, is any heat going to flow between objects? No. If you and your surroundings are exactly the same temperature, you're not going to be no heat flow.
It's like touching your own hand.
Right. Yeah. Anyone need more time? We have one more slide. We good over here? Well, again, your hands are colder than the internal inside your body. Your surface skin of your skin is colder than the internal part of your body.
But it's not water.
What? Well, you have lit air and liquid. Like it's coming from inside of you, so it's warmer than the outside. You guys, we're good? June, you're talking, so I guess you're done. So, now heat always flows from a higher to a lower temperature. It's kind of like water. Water always goes from a higher level to a lower level. We always fly from a higher to lower temperature. And energy is going to keep flowing until temperature is equal. When temperature is equal, we say we have reached thermal equilibrium. Remember that word? We've seen that word before. Equilibrium. There, we talk about forces. We are in equilibrium when the forces are equal, right? Equilibrium when torques are equal. We're in equilibrium. Same idea here with the temperature. In other words, you are constantly losing energy to this room. Why? Because you are basically 98 degrees and the room is about 70. So you are constantly losing heat to this room. Okay? And then you will keep losing heat in this room until everything in this room is the same temperature as your body. And since you are an endothermic being, you generate your own heat, you have to wait until everything else heats up. I mean, when I get to the room in the morning, this room is basically at equilibrium. Everything in the room is the same temperature. The heater's been on for about an hour, so everything's had a chance to reach equilibrium. Now, as soon as I get into the room, are we at equilibrium anymore? No, because I'm warmer than the rest of the room, so the room is no longer at equilibrium. On that. All right, that's all we are, so write your summaries. For the remainder of the period, I know there's about 8-7 minutes. Work on your vocab. Work on, remember, you write your sentence from the book, write a thing, and you get it done, have me stamp it. Otherwise, take it home as homework. So, you know, and by the way, and lecture notes you keep.
Oh, yeah, I just want to take it.
That's fine. Keep all the lecture notes. Yeah. So if you haven't done, have me stamp it. Otherwise, finish it and have me stamp it next time. Remember, they do go in your packets. They do go in your packets. Where were you in your thesis classes? What had you talked about?
It's a long story.
Well, look through the book and figure out where you are. Basically, they've done the first 14 chapters.
Yeah, I know that.
So whatever you haven't done in those first 14 chapters, you are responsible for it. Because I know it depends on who what teacher. I know Mr. West doesn't do energy until later on. So I don't know why. But what?
But I'll explain that.
Okay. I need this back. We can do that. We can actually decide on a safety contract. Last safety, we got that before we start.
I can get it.
Well, this next time, this is the class policy, and then you guys sign that. They did all this beginning of the year. By the way, safety equipment, because we are, most of the stuff class we do deal with hot water, boiling water. You really want to wear long pants, closed-toed shoes. This is actually the lab that actually got boiling water dumped on me and things like that. These labs. Reads. Yeah.
You need to bring your own books.
You need to bring your own book.
So like,
You need to get your own. That you get from the textbook.
I'll bring everything.
Every day. especially since we're doing starter. There, when you guys get done, put your books back in order. I'm sure we can all count to 23, right? When you are finished. You guys shouldn't be turning them in now because you're not finished. Once you are finished, and then I will stamp it. You can put your book back. Which means you were doing this while I was talking.
No, while you were doing the notes, when everyone was still writing it down.
Okay.
You see, I'm using my time wisely.
Good. And when did we reach that epiphany?
What epiphany?
That we should use our time wisely.
Oh, I've had that forever.